Hello, and welcome to today's webinar, It's About Time, PNT Challenges and Benefits of Multi-Constellation and Multi-Signal GNSS, brought to you by GPS World and our sponsor of the event, Talisman. Talisman is a developer, manufacturer, and provider of GNSS, Iridium, and Global Star antennas and accessories in support of customers who are engaged in a broad range of satellite-based positioning, navigation, and data applications. I'm Mackenzie Schoner from North Coast Media, content marketing producer for GPS World, and I will be the moderator for today's event. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it into the panel's text box, then click Submit to place your question in queue. We encourage you to ask any and all questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and Assistant Producer Aurora Harris or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of your console. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see at the bottom left corner of the screen. You may download a version of the slides from today's presentation and the Resources widget, as well as access to the Talisman website and the GPS World website. Now I'd like to introduce you to today's presenters. We will be hearing from Julian Hoepker, Director of GNSS Product R&D for Talisman Wireless. After a 4-year postdoctoral training, Julian joined Talisman Wireless in Ottawa, Canada as an antenna and RF engineer and is now the Director of GNSS Product R&D. We will also be hearing from John Fisher, VP of Advanced R&D for Aurelia. For almost 20 years, John has been working with global navigation satellite systems, wireless positioning, navigation, and timing, and specialized systems for customers at Aurelia. We will also be hearing from Sunil Bisnath, Professor of Geometric Engineering at York University. For over 25 years, Sunil has been actively researching precise GNSS-focused positioning and navigation solutions and applications. At this time, I'll turn the presentation over to Sunil. Take it away.
Thanks, Mackenzie, and hi, everyone. Thanks for joining us on this webinar. Hopefully you'll find lots of interesting information from our 3 talks, and we look forward to taking your questions. So I'll focus on the P and the N part of this webinar, and John will follow me talking much more about timing. So first of all, just a few words about York University and our lab. York University is in Toronto, Canada. It's the nation's 3rd largest university with about 55,000 students and over 7,000 faculty and staff. And we just try not to get confused with the University of York, which is in the UK. The GNSS lab was established in 2006 by myself within the Geomatics Engineering program. And we focus on GNSS measurement processing, sensor fusion, software and hardware receiver design, and many scientific engineering and mass market applications. And our people, as you can see by our logo, really are our strength. So in terms of GNSSs, currently we have, of course, GPS, the standard bearer, GLONASS that has been with us soon after the introduction of GPS. Newer systems include Beidou, or BDS, from China, and Galileo from the European Union. We currently also have a number of regional systems. The regional version of Beidou tend to be referred to as BDS2, the QZSS system from Japan, and NAVIC from India. And I say current because there are plans for potentially other additional satellite navigation systems. What does this mean? Well, this means if we were to add up all the medium Earth orbiters that are the satellites from these constellations that orbit the globe, as well as the geostationary and geosynchronous satellites, we have over 132. We have 132, which is quite a significant number. However, I would focus on just the MEO, the medium Earth orbiters, in this talk, because these are the satellites that everyone around the world sees. And we are now in a situation where we have over 100 global navigation satellites. So it's quite a milestone. So what does this mean in terms of the effect of multi-GNSS on terrestrial users? Well, first let's take a look at satellite availability. So what we have in these plots are the number of satellites that are visible on average over a day. If we were looking at all the satellites 10 degrees above the elevation horizon and beyond. And at the top left, what we see is GPS, and then we keep adding constellations. So the warmer the figures get, the higher the number. And the range here on the scale is 0 to 40 satellites, and so 0 in dark blue and 40 in bright yellow. So with GPS, what we see is a nice global coverage of between 5 and 10 satellites. When we add GLONASS, that number jumps up into the high teens. When we add Galileo, we're already at the 24 or so satellite level, and by adding BDS2 and 3, what we see globally is up at around 30 satellites that we can observe at any given time, and all the way up to over 40 in the Asia-Pacific region. So multi-GNSS really has a huge impact on satellite availability. If we go dig a little further and look at the impact on measurement geometry, so that's the geometry between the satellites and the user on the ground, we can use PDOP, for example, position dilution of precision, as a good measure, which is a unitless number. And in this case, the range is from 0 to about 3, and it's an inverted scale. So the lower the number is, the more precise we would expect our measurements. And what we see with GPS, a fairly good PDOP. It's a little lower at the poles, as we'd expect because of the geometry. But about 2, 2.5. We add GLONASS, that number goes down by about 0.5. We add Galileo, it goes down another 0.5 or more. And by the time we are using all 4 constellations, the PDOP is way down to about 0.5 or so. So tremendous improvement in measurement geometry by using multiple constellations. Another way to look at this is through satellite visibility plots, so the sky plots as we call them. These are polar plots. This one happens to be a particular location where I am in Toronto, Canada. And what we have in the 4 figures are the locations, the elevation angles, and the azimuths of the satellites that we'd observe above 10 degrees. So GPS, then we add GLONASS at the top right in red, we add Galileo at the bottom left in yellow, then we add Beidou at the bottom right in purple, and we can see as we layer the constellations one on top of the other, just a huge increase in the number of satellites. So this really does help when we have, for example, obstructions like buildings, etc. The more satellites we have, unless the obstructions are ubiquitous, we can see nice improvements. So let's move on to the signals. For For many, many years, most users were single frequency users, and their options were limited. It was GPS L1 or the GLONASS frequency. During that time, performance users had the option of dual frequency receivers and antennas, and so they would be able to track signals from GLONASS and GPS on L2/G2. That has since changed. Those days are way behind us. And in our multi-constellation, multi-signal world, we see something like this, where we've added the Galileo signals, we've added the Beidou signals. There are more than two. What I've done in this figure is I've basically color-coded the signals into 4 bands. We also have, I should have mentioned, the frequency, the bandwidth, wavelength, and the code modulations that are on top. So we end up with a plethora of signals and and modulations that we can make use of. A word about the strength of the signals. Here we have, for those constellations and modulations that are publicly available, the minimum specified receiver power in dB watts from those constellations. And what we can see is that, given that that is a log scale, is we can see the strength of the signals, and it gives us an indication of our ability to acquire and track those signals. The one standout really is GPS L5, and that's for 2 different models that we see there, and we see a significantly stronger power. So what are the challenges then, given that we have all of these constellations and we have all of these signals? Well, we can look at there are many, but we can categorize them into sort of 2 components. One, in terms of signal processing. So our antennas have to change, and Julian will give you a really good presentation on antennas soon. So we need to expand to the multiband sensitivity of these antennas, and then we have to deal with the out-of-band interference and suppress that. So we want to accept more, and we need to constrict what we accept. On the receiver side, we have to deal with signal compatibility and the interoperability between the signals, between constellations. So a much more complex receiver. We have to deal with signal interference, jamming, and spoofing. And there are pros and cons there, some of which John will talk about. And then we have to deal with the limited processing power on the receiver chips. If we're going to track many more constellations, many more frequencies, how do we manage that? Then, on the measurement processing side, we have an analogous set of issues to deal with. We have variations in the reference systems between the constellations. So these are the spatial reference systems, for example, different reference ellipsoids being used by different constellations, different temporal or time systems that are being used by the different constellations. And so the user processing software has to account for these spatial and temporal offsets, and they can be as many as tens of meters in magnitude if we don't. Also, there are many signal biases between modulations on a signal, between signals or frequencies on a constellation, and between constellations, such as differential code biases or DCBs, satellite group delays, and other biases. And again, the user processing software must account for these biases, as they can have centimeter to meter magnitudes over time. Some of them are more stationary, others drift over time. So without accounting for these, we would have problems in terms of combining the measurements from different constellations. So let's take a little deeper look. So in this figure, we're trying to illustrate the effect of signal obstructions on multi-GNSS. And what we have here is a global PDOP, that is a set of global stations and the average PDOP that we would see with different elevation masking. And what we have in the top left figure is the situation for GPS when there's a 10 degree, 20, 30, and then 40 degree elevation mask. And these are histograms. So what we see on that top left figure are the number of occurrences of a particular PDOP value ranging between 0 and 20, again, where the lower the number is, the more precise the positioning would be. And what we see is as we raise the elevation mask in the top left from 10 degrees all the way up to 40, what we see is that the PDOPs get worse. So our expected solution gets worse because our geometry gets worse, because we're using fewer and fewer satellites. There's more and more blockage is what we're simulating. Well, what happens when we add, for example, GLONASS, and we use R, G for GLONASS, G for GPS, R for GLONASS, E for Galileo, and C for Beidou, following a particular convention, so GREC. Well, when we add R, that's GLONASS, to the top right figure, what we see is the histogram shift to the left. The PDOP becomes more precise. When at the bottom left, when we add Galileo, we see a further shift to the left. And by the time we get to the bottom right figure with the 4 constellations, we see much, much better performance and a further shift to the left. So adding constellations can help us deal with signal obstructions. And in the table we have there, what we see is, I use the example with the two green circles, that if we had a mask of 10 degrees, a blockage of 10 degrees, and we had just GPS and GLONASS, we would have an average PDOP of about 1.4, which would be very similar to if we had a 20-degree elevation mask, so a bigger blockage, and we have 4 constellations. So having the 4 constellations would give us a performance similar to the 2 if we had a bigger obstruction. More telling are the blue circles. A GPS with a 10-degree mask. Well, what happens if we had a 30-degree mask? Well, if we had all 4 constellations, we'd get almost similar geometry. So we could have a much bigger obstruction and do reasonably well with the 4 constellations versus the 1. Okay, so let's take a look at some positioning results. What we've done here, one of the areas our lab focuses on a lot is precise point positioning, or PPP, which is a wide area augmentation processing technique that doesn't require local calibration or reference stations. The major limitation for PPP is the time for initial convergence, which could it could take tens of minutes to get from meter level down to centimeter level or better. So what we've done here is taken 1 week of global stationary geodetic data, so high performance antennas and receivers that are static, and we've processed them in kinematic mode, so we assumed they were kinematic. And we define convergence as the time it takes to get to 10 centimeter horizontal error. So, and we've put in the 95 percentile results here. And I should point out we're not including BDS3 in this particular solution. And what we've done is we've produced what are called the float ambiguity solutions. These are the carrier phase solutions that are floating point estimates. And we've also then when we're able to fix them. And what we see is in the figure at the bottom left is it takes about 15 minutes with GPS only to get to this level of precision. And if we fix, we get down to less than 10 minutes it takes to get there. And when we add constellations, we see improvement. So adding the constellations allows us to have better float solutions and better fixed solutions, all the way down to about 5 minutes to get the solution, which is not quite RTK performance, but it's getting there. But these are dual frequency results, which leads us to the next slide. What happens, these are the 4 constellations, what happens if we go from 1 to 4 constellations, but now add additional frequencies? And what we see in this figure is a slightly different data set, and we are including the BDS3, again 95% results, and what we see is that there's huge improvement in the fixing by adding constellations. So dual frequency, 3.5 minutes to get to that convergence, triple, we go down to 2.5 minutes, and quadruple where it's available, and in this case, it's really the Galileo satellites, because we weren't able to get the corrections for the fourth frequency in BDS3, 1 minute. So pretty close to instantaneous convergence by the time we get up to the fourth frequency in PPP. And you are starting to see products and services out there that have such tremendous performance. So in conclusion, challenges? Yes, there are challenges in terms of hardware and software design, but these changes are being met, and you'll hear more about them in this webinar. Benefits? There's a great list of benefits in terms of accuracy, availability, integrity, and resilience, and these are very significant benefits. So with that, I'd like to end my portion of the webinar and pass things over to John. John?
Thank you, Sunil. That was great. And as you said, you'd focused on position and navigation. So I'm going to focus on timing applications, and the challenges and benefits of this multi-constellation, multi-frequency capability that's emerging. So let me get started. First, before I start, let me just tell you a little bit about Aurelia. If you don't know us, of course, we very involved in timing and synchronization systems. We make atomic clocks. All the atomic clocks, for example, in the Galileo system are made by Aurelia. But we also do more. We do test and simulation of GNSS things. We even do search and rescue emergency beacons for aircraft, for ships, and all kinds of customs solutions. So working in aerospace, defense, commercial markets, any place where there's a critical need of where you have a PTP solution that you can trust. So that's what we do. So enough about us. Let's go into a little history of timekeeping and its relationship to navigation. So I'm going to go back in time a little bit here. So a little bit of history first. I'm going to start with the fact that how was centuries ago, how was navigation done? Done by as soon as you got out into the seas where you no longer had land reference points, no landmarks to look at, you used the stars. And so you'd map out the stars when you knew where you were, so that then as it varied over the year, as the Earth revolved around the sun, you'd have a map of the stars, you'd know where you are, and you'd be able to determine where you are on Earth. That worked fine for latitude, but as we all know, the Earth spins. So, and it's spinning at approximately, depending on your latitude, 300 to 400 meters per second. And so now, unless you know what time it is, with less than a second, you're not gonna know your position very well. And so, that was a bit of a problem, and especially when global navigation started to become popular in the 16th century after Columbus, Magellan, and all of those folks started to navigate all around the world, and they needed to do this navigation, and that was a big problem. That celestial navigation wasn't very good, and so the kind of accuracy you get with like mechanical clocks, you'd have to know what time it is so that you know where your reference is, and the kind of accuracy you could get in those days was like 10 to the minus third. So, which meaning again, given the speed at which the Earth is spinning, hundreds of kilometers you could be off if you're using that method. So the British recognized this in the 18th century. In fact, we refer to Greenwich Mean Time because it was established. That's where our the Greenwich Naval Observatory is where we've established the prime meridian, the longitude prime meridian, because they were very much that's what they were trying to establish, where we are in longitude. And so, in fact, as a side note, if most of us navigation geeks have visited that nice museum there, you can stand at the museum. You can see some of the old mechanical clocks that they used to use, and actually stand across the prime meridian, take your picture of that you've been in 00. But I digress. I'll get back to the subject here. So here we are in the 18th century, and the British Naval Observatory awards a prize to say who can build the best clock to solve this problem we have, and they did. This chap named Harrison built this clock in 1750s. He's actually about 3 different versions, but he won the prize and is able to increase accuracy by 2 orders of magnitude, which is pretty impressive, and getting him into the few kilometer accuracy. So that was a big plus. So now we get to the 20th century. We have quartz technology, and in your phones and your watches and stuff. Since that, you can get very good 10 to the -6 type accuracy. So if you're still doing celestial navigation, you could even use your clock, your watch, and use that. Of course, by the second half of the 20th century, we now have atomic clocks, and we can do much better. And in fact, that might be a subject for another webinar some other time. But now let's take a look at now. What does all that have to do with our GNSS system? So if you look, satellites. It's not very old. The first satellite was launched the year I was born, so I don't think of that as being that long ago. Some of you might think it's older, but we get the 1957. We get the first satellite. 1967 is when we really adapt things of measuring time by atomic clocks. We've even redefined a second. Now at that point, saying, okay, it's no longer the movement of the Earth, what we call the astronomical ways of measuring time. We use atomic theory to measure time, and it's an extremely accurate way of doing it. We come up with what's called universal coordinated time, which is through treaties of 190 countries, all signed treaty at that time to say, hey, we'll agree on using that for time. So now we have that, a great way to measure time. We have a way of putting satellites up. So the GPS system is born in the 80s. And so this is, many of you in the audience I know already know about GPS and GNSS systems, but for some of you that are new to this, I'll just quickly explain how GPS works. They're all the GNSS systems. What they do, the satellites don't know where you are. They're not tracking you. They are just transmitting a pulse, or the electronic equivalent of a pulse, a high correlation peak thing there. But it's the equivalent of a pulse, and they're transmitting it once every second, all exactly at the same time. And when I say exactly, I mean within less than a nanosecond of synchronization. They all transmit that pulse at exactly the same time. You on Earth with your receiver, you receive those pulses at different times based on how far away you are from the satellites. So you can measure your distance by measuring those time differences. You can measure your distance to the satellites. You know where the satellites are because they tell you where they are in their data messages, and so you can then triangulate and determine where you are. You have 4 unknowns in this situation, X, Y, and Z, where you are, and time. You just know that they're all doing it at the same time, that their differential is near 0, but you don't know what time it is. So if you get 4 independent measurements, 4 unknowns, you can solve for position and time. So that's how it works, and so that's why we measure both position and time off of these GNS systems. Very accurate. Prior to the year 2000, the GPS system wasn't that accurate. We had the U.S. military put in this actual noise capability that only the military could avoid. Well, in the year 2000, the Cold War is over. They decide to turn that off, and so then even us civilians are now able to get this high accuracy. And so here we are today. As we said, we not only have the GPS system, but all of these other three very good, very accurate systems. So that's where we are, and so companies like us at Aurelia and other companies will use the GNSS signals not only for positioning but for time, this precise time, taking advantage that you've got these very good atomic clocks circling the Earth, as Sunil had pointed out. Over 100 now pointing with transmitting precise time to the Earth. So you can take a device, in fact, we call it a time and frequency server, which you extract the time from these GNSS signals and then put it to use. Extract the time and the first derivative of time, which is frequency, and put it to use for synchronizing things, synchronize data centers, all the distributed processing that we're doing by processing things in the cloud. Google is all of its servers needing to synchronize things together, so you do that. Anything that transmits a signal that is a receiver transmitter, a radar, a digital TV transmitter, the cellular base station transmitter. They need precise frequency and precise time, and so this is a great way of doing it. And lastly, power grid. There's several others, but these are the main ones. The power grid, synchronizing the power distribution across the grid. So now. I always say the GNSS signals are great. They're very accurate. They're wonderful when you can get them. The big problem is they're being broadcast from 20,000 kilometers above the Earth's surface. The signal, when you receive it on Earth, is very weak. It's very weak, so it's two main problems. Is one, it makes it very easy to jam, either unintentionally or intentionally, from some bad guy. And number two, these are open systems, at least the civilian ones that we're all using, so it can be spoofed. Some people can make a fake signal and fool you. So those are the two main problems. So what do we do about it? How do we refer to making things more resilient? So with a time situation, one of the things we do is we install what we call a holdover oscillator. And atomic clocks are no longer these exotic devices, but they're actually commercially practical, becoming very small and affordable. So in our time service, we'll put in even an atomic clock holdover oscillator so that even if the GNSS signal gets interrupted, you can still carry on. You've disciplined or phase locked your local oscillator to the GNSS signal, so that if it disappears, you can still maintain time. The other thing we do, and Sunil had touched on it, and you'll hear a lot more about this from Julian in the next talk, is using we call smart antennas, anti-jam antennas. In fact, we use the talisman antennas very good. The fact that, as Sunil showed, you can put elevation blocking at the horizon, still pick up, because there's so many satellites, still pick up a very good GNSS signal. But blocking the horizon, that's where most interference is coming from. Most interference is terrestrial based. So if you block the horizon, you can do things really well there. And then even from that, there are even other tracking antennas. We call some real smart antennas, which will automatically steer a null towards an interference, or maybe make a high gain directional beams of which track the satellites as they go across the sky. So all these kinds of things that typically those are called SERPA antennas, or controlled radiation pattern antennas that you can electrically control. But I did say encrypted signals are not available to the civilian world. That's been true up until now. The Galileo system is offering, I guess, for civilian use, what they call the OSNMA, the nav message authentication. And so that way you can, much the way HTTPS is authenticated when you're on a website, a similar idea to do that with the navigation messages that you're hearing. So I think we'll be seeing that available soon, but that gives you a measure of protection. So lastly, let's talk about not only multi-constellation but also multi-frequencies. What are the advantages from this point of view? Senel had showed a number of advantages in the navigation, the improved GDOP, PDOP advantages. In general, if you use more frequencies, more of these frequency bands, it'll be harder to jam. The bad guy now needs to jam 3 different frequencies instead of just 1. So there's an advantage there. Or interference, unintentional interference, tends to be just in one band. It doesn't tend to be a unique circumstance of where it's being in all bands. Besides all the advantages that you heard before about multi-constellations, the other thing is that there's a glitch in any one system, and it's not unheard of. In 2016, the GPS system had a glitch. Two years ago, the Galileo system had a glitch in it. That things will happen like that. So you get more diversity, more resilience that way if there's a fault in any one system. On the negative side, the part of that they're all in the same band makes it it's still easy to jam. It's not that much different. If one gets jammed, all of those signals, all those constellations are getting in that band are getting jammed. So there's an issue there. And the other thing is, as much as say, okay, if you have more complexity, if someone wants to spoof you and you're using all 4 GNSS systems, they'll have to spoof all 4 of them. So that makes their job harder. But on the other hand, the simulators, and we know this because we build simulators, we build good ones, that they're getting better all the time. It is possible to simulate all of them simultaneously. So those are the main things you've heard about the difference in time scales. So it's something to remember whenever you're using multi-constellations, knowing that each constellation has its own unique time scale. So when you're working down at the nanosecond level, you want to be aware of that. So that's all I'm seeing. I'm starting to go a little over time. So with that, I'll stop and turn it over to Julien. Thank you.
Thank you, John. Hello, everybody. I am Julien Hooker, and I'm the director of the GNSS product R&D at Talisman Wireless. I'm going to continue this presentation, concentrating more on the antenna aspect of multi-constellation and multi-signal GNSS. So just a brief word on Talisman. Talisman is a Canadian-based company. We are part today of the Calian Group, and since the beginning, we manufacture precision GNSS antennas. We have a wide, broad catalog from affordable dual band to reference grade antennas. And our mission from the beginning has to be to reduce the cost by design. The idea that during the last 10, 15 years, we saw the cost of receivers going down, and it makes sense that the cost of the antenna would follow, but we try to do this without compromising on the precision. So what is the importance of the antenna? One thing we'd like to remind to our customer is the GNSS antenna is the first component of your GNSS system. So if the antenna receives interferences, if it produces noise, shift phases, there is a very limited amount of things that the receiver can do to recover signal degradation. So the GNSS antenna is just the first line of defense of your system. This is why the antenna design, choice, installation is really critical and should be done wisely. But what's a GNSS antenna? So inside we have two main components. We have a radiating element, which is a passive component, and we have what we call the low noise amplifier, or LNA, which is an active component. And they both will play a role in this signal processing. First, the passive radiating element will receive the wave from the satellites, and it will amplify or attenuate depending on its gain irradiation pattern, and transmit the signal to the LNA, which will also amplify, perhaps add noise depending on noise figure, and we'll also have some different characteristics to look at, like the saturation point of rejection. When this is done, the signal is sent to the receiver. So what is the role of the antenna? Typically, the radiating element and the LNA will work as a team. And the idea is to do two main things. First thing is to maximize what we call the G over T, which is the gain of the antenna over the noise temperature of the receiver. And the idea is to amplify the carrier to noise ratio to make it highest as possible. So we're going to amplify the GNSS signals and limit the in-band noise. The other main thing to do is to protect the receivers from any out-of-band or in-band rejection and transmit clean GNSS information. So for that, we're going to try to attenuate out-of-band interference, and if we cannot attenuate them because they will be in-band, we're going to try to limit saturation and stay in the linear mode of the LNA. So what are the antenna requirements for having a good GNSS antenna? First, the key thing is to have a right polarization. The polarization from the satellite is the right-hand polarized, which means the antenna should be designed in order to receive only right-hand polarized. This is different from linear antennas, which is used for Wi-Fi, Bluetooth, cell phone, things like that. Here we're talking about a circular polarization. And in this situation, it's right-hand circular. The left-hand circular is also important because we want to reject it. And the reason for that is when signals are not arriving directly to the antenna and they bounce against buildings or trees in the environment around the antenna, they will affect the circularity of the polarization, and they could flip the circularity and become more left-hand or elliptical. So by, in fact, rejecting the left-hand polarized signal, we're going to reduce the multipath effect on the antenna and get a cleaner signal. We also want to have a high efficiency and a low noise figure. So this is related to the aspects I talked before about maximizing the G over T. For modern application today, like RTK or PPP, one key thing is to also minimize what we call the PCV, the phase center variation. So the phase center is a point in space where the signal are arriving and received at the antenna. And this point in space is in fact moving depending on the elevation angle and depending on frequency. So as it moves, typically it will induce a phase error in the signal. So it's very important if you want to have a precise measurement of where you are to have this point to be as fixed as possible, because this point is typically the beginning of your tape measure between your antenna and the satellite. So you want to minimize that phase center variation. And another key thing, which seems obvious, is to reject any out-of-band interfering signal. So at the beginning, like Sunil and John said, we had just dual signal on GPS, two frequencies, one at 1575 and the other one at 1227 megahertz. Today, we are talking about multi-constellation with 4 different constellations and plenty of signals. So the antenna needs to adapt. We need now multi-constellation antennas. So everything we talked about, the antenna requirements, still has to apply not only for L1 and L2, but it has to apply for a much wider frequency range. So we need to keep an antenna which is as performant as before on a wider frequency range in order to keep the same performance, same quality of reception, and for a higher GNSS robustness. So at the beginning, let's go back. What were the solutions? We had 2 frequencies. We could use like a standard stack patch, compact thing with dual feed in order to minimize multipath. And by using those patches are quite good because the frequency range you're trying to cover is quite small, so you can maximize the efficiency by tuning your antenna at the right frequencies. And if we see here the efficiency variation of the frequency, we can see that we have a peak of efficiency just on L1 and L2, and you will get just good results and your system is fine. But now if we go onto GNSS, we are widening the frequency range, and now you can see that the efficiency of your antenna is not constant over frequency, and this is where you're going to start to lose quality of the signal if you're tracking more signals over more frequencies. So what does that mean? It means that we need to look at new antennas, and especially new antenna technologies. You can use bigger patches, so bigger patches will increase the bandwidth of smaller, compared to smaller patches. You can go to helix antennas, and you can also go to antennas which would be perhaps dipole-based. We can see on this graph the different type of efficiency versus frequency that you can get from helix patch and our Verostar technology, which is dipole-based technology, which is the one which gives us best performance in terms of efficiency versus frequency. But here the big challenge is that the frequency you're going to receive depends on the wavelength, and like Sunil mentioned, the wavelength is about like 190 millimeters, around like 20 centimeters. So to reduce the antenna, you reduce the size, you will typically change the wavelength. So the challenge is how to keep the same frequency response by reducing the antenna. So we have techniques to do that. Things are changing every year, and we introduce new antennas. But today we are able to propose like different packages and different formats to be able to receive multi-constellation and multi-signal. We are working today on a low-height, full-band helical because people always want something smaller and more compact. But this is one of the key challenges of antennas today. Another thing we talked about interferences. So again, at the beginning, when we're just getting over L1 and L2, perhaps interfering signal were a bit further on the frequency range and were not really affecting the signal of the GNSS, so that was fine. But now we are widening the GNSS spectrum, and now we're getting more and more closer to a really strong signal, which are terrestrial signal like Iridium 1616 to 1626, or Ligado, which is a recently added signal, which will be from 1525 to 1536. And we can talk about like Japanese LTE. There are also new LTE signal in Europe today, which are jamming all the system. We have new compliance to meet, like red compliance, which are forcing rejections of amplification on the LNA for specific signals. So this needs to be taken into account when now we're designing the antenna. What does that mean? It means we have to work on the filtering of the LNA. So the idea will be probably to cascade filters. And this works. When you cascade filters, you increase the rejection out of band. And this works fine, but you have to be careful because now you're going to probably look at some trade-offs, and I will go in details just after that. But the idea is like usually we're going to try to go now on custom filters. We're going to be made for specific antenna and band, or perhaps also area in the world which have specific signals. But by looking at custom filters, we have better control of noise figure, the rejection levels, and group delay variations, and temperature variation of the filters. If you look at it a little bit in the details, like if I'm cascading filters, I said I get better rejection and sharpness is important if the interfering signal is very close to the GNSS spectrum. But by doing this, I also degrade the flatness of the gain in band, for example. We are amplifying the imperfection of a filter by putting 2 or 3 in a row. Same thing with the group delay. If I need a flat group delay over a specific spectrum, like for example GLONASS, which will be very sensitive to that, adding more filters, I amplify the group delay variation, and here I'm introducing issues. If my filter vary in frequency, the response vary in frequency, I can now start to be not rejecting interfering signal which are very close. That's why we need to keep an eye on all those aspects when you design your LNA. Here an example about the importance of the group delay stability. We talked about GLONASS just like between the band like 1598 and 1606, and we'd like to minimize those group delay variation. For example, here is a group delay variation over frequency for an antenna we had, which has good rejection, but we had a group delay variation over G1 of about 9 nanoseconds and a differential group delay, which is the group delay variation between L1 and L2 of about 8 nanoseconds. And this is important for ionosphere corrections, for example. But if you want to just add filters on this antenna in order to have better rejection, what's happening if I add a filter on L1, suddenly the group delay over L1 is increased, and now I have a group delay over G1 is almost doubled. I go 19 nanoseconds instead of 9, and for the differential group delay, I go from 8 nanoseconds to now 25. So this has a huge impact on the performance of the antenna and the system. So this is things that have to be looked at when you design the antennas. Let's talk about another aspect, and John mentioned it a little bit, is about radiation pattern shaping. The idea comes from the fact that most of the interfering signal come from the ground, so it means low elevation angles. So we're going to try to, in fact, attenuate the ground plane, the radiation pattern at low elevation angle in order to attenuate the response to those interference. So here is the design of L1 antenna, which is an anti-jamming system, and we try to reduce the gain of the antenna at an elevation of 10 degrees by about 25 dB. And this has for effect that all the interfering signal have been attenuated. So this antenna has been tested on a roof close to a truck facility, and with a standard antenna over a period of 8 days, we lost the signal for about an hour and a half, where with this solution, we just lost the signal for 41 seconds. So this was very efficient in a way to prevent interfering signal. And we're always working today on a L1, L2, L5 antenna because we're definitely talking about a multi-constellation and multi-signal world. So as a conclusion, I would say that the choice of the GNSS antenna to use is very, very critical. Multi-GNSS and multi-signal, we're talking about wideband antenna for those modern applications. We're going to have to look at new technologies if we want to keep a high efficiency, good circularity, and small phase centers. Controlling and customing the filters is more and more important today in order to protect against interferences, control group delay variation and temperature variation. And looking at radiation patterns shaping is also a solution that could be used in some situations. Just as a wrap-up of those three presentations, I would say that multi-constellation, multi-GNSS has existed now for a few years, but not everybody has adopted it. So the question is why an L1 user should go L1, L2, or why an L2 should go L1, L2, L5? Why should we go to multi-constellation and multi-GNSS? So we think that it's needed in a case where you want a more precise, a more accurate and faster system, and would perform still very good in more complicated environment all over the globe. You will usually be more resilient and more robust. It's true that the complexity increases, but today the technologies are evolving and solutions are already here. So if you ask us if it's worth the effort or the cost, we definitely think yes. And on that, I will give it back to Mackenzie. Thank you.
Great. All right. At this time, we are going to jump into some questions we received during registration and a couple we got during the presentation. All right, my first question is for Sunil. What's the 5-year outlook into the future for GNSS?
Thanks, Mackenzie. It's a good question. It's a very broad question, but what I would say following on Julian's last comments is that we're seeing more of an acceleration of what we've been seeing over the last few years. More multi-constellation, more multi-frequency, greater adoption of what we would have called the professional grade hardware, antennas, receivers, and software into more and more mass market applications. So further transition into multi-constellation, multi-frequency, and further penetration of higher performances in more mass market applications. That's a general answer, but it's a very broad question. And if others would like to chime in, please go ahead.
I think you covered it, Sunil. Yeah.
Okay. My next question is for John. What is the accuracy of a timing offset between a different constellation?
Okay. Yeah, as we mentioned there, each constellation is using a different time base. Now, the differences are in the order, we're talking nanosecond, sub-nanosecond type issues, but they will go into your error budget. So it's a rather complex thing. I guess I can't say exactly what it is. It's a time varying thing. I guess just 2 points to remind people would be one. Each constellation is giving you information of how it compares to UTC, the Universal Coordinated Time. So that's a more generalized time base used throughout the world, and then each constellation uses its own thing. So you have GPS time, you have Galileo time, etc. And so there's a comparison between those. And I guess the other thing is the behavior of the receiver themselves. The newer receivers, the multi-constellation receivers, some of them are allowing you to set which time base you want to use. But as you switch from one to other, there's some modes that may not be enabled. And so I guess the thing I could say is that it's in the nanosecond, sub-nanosecond area of the differences, but there are even calculation things of where you might not be able to use certain modes because of these different time bases.
Interesting. Okay, my next question is for Julian. How can we build low power receivers 1 to 2 MAB with multiband GNSS?
So on this question, for the receivers, I won't be the specialist here, but I can say that for antennas, we are able to limit the current consumption of antennas, and this is a rule we try to do at Talisman. We're trying to use low current consumption LNAs in order to minimize the consumption of the full system. And we already developed in the past like very low consumption antennas, like just using like 2 milliamps for like single frequency antennas. But today we are able to do like triple band antennas, and I think we're just using about 12 milliamps. So this is the aspect. On the receiver side now, I won't be the person to answer that because we're not building receiver directly at Talisman.
Okay. My next question is for Sunil. How does multi-constellation GNSS help or not help in heavy tree canopy?
Interesting question. So what we showed earlier in the webinar were examples of of binary situations where you either had a signal blockage or no signal blockage. And what we would see in tree canopies, depending how thick they are, the situation isn't as binary, it's more fuzzy. So the real benefit comes from, if it's very, very heavily treed canopy, we're going to have problems. But if the canopy is thinner and some signals can make it through, the benefit of the multi-constellation, multi-frequency is that we would, depending on what your performance specifications were, we would be able to receive enough signals to produce a reasonably precise solution, a positioning solution. One of the other benefits with some of the frequencies I've mentioned, for example, GPS L5, is it's transmitted at a higher frequency, so higher amplitude. So with some of the signals, there will be a higher percentage of the signals that will be received and be able to be acquired, sensed by the antenna and acquired by the receiver. So there are benefits in terms of the number of frequencies, the specific frequencies, and just the sheer number of measurements that you're able to try to acquire and track.
Great. All right, my next question is for John. how is regulation likely to evolve for the establishment of standards for resilient PNT in the U.S. and worldwide?
Oh, okay. I guess I could maybe speak for the U.S. and at least what I see going on in the U.S. right now. Some of you may be aware, last year an executive order came out from the White House of telling our critical infrastructure components and other agencies across the United States for aviation, for the power grid, for the telecommunications, for financial institutions, an order that said they need to build in resilience when using PNT services from GPS. And so our Department of Homeland Security had come out with an actual standard, a framework for resilience to define what do we mean, and they define like 4 levels of resilience. So it's a real nice standard. Our NIST, the National Institute of Science and Technology, that establishes a lot of our technical standards, come up with some cybersecurity standards. They do that, and also for how to protect against GNSS. So it's a pretty involved topic. I guess I could point people to, if you visit our website, we've done a number of actually webinars on this subject, and you could listen to those webinars if you visit the Aurelia website.
Okay. Julian, I have another question for you. Is there any use case where L1 has advantages over L5?
In this situation, I would say that, to me, one of the advantages I see today is I think there is still a lot more L1 satellites in the sky compared to L5. So it's true that L5 has more power, but the L1 satellites are still the natural signal that goes with every receiver, as far as I know. And usually when we're talking about multi-frequency, it starts with L1. So we're talking about L1, L2, or L1, L5. We're also talking today about like some L1, L6. So it's difficult to have L1 being removed. I think there is companies working on L5 only receivers I've heard of, but I've not been involved really with this directly. So I'd be interested to know why some people would not use L1. But up to now, I think it's one of the major signals, and I think it's still going to be used for many, many times.
Okay, great. That is all the time we have for questions. So to just round it out, thank you for attending today's webinar. It's about time, PNT challenges and benefits of multi-constellation and multi-signal GNSS, brought to you by GPS World Magazine and our sponsor of the event, Talisman. If you have any additional questions for myself or our speakers, you can reach out to us directly via the email addresses you see on the screen. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to that page. Thank you all for attending, and we hope you'll join us for another great webinar.